Okay, so now we're going to continue this lecture about this abstract idea of the covariant derivative of the vector field A with respect to B. Now I'm going to leave the notation just like that. I'm not going to go with this and this and this anymore. And of course we understand this is a full vector field, and B is also a vector field perhaps, but its value at the point P is important. We'll get back to that in a moment. So we're going to sort of understand it all. We're going to start taking this and speaking of it in an axiomatic way. We want it to be a derivative. So we're going to have to say, okay, what if we make certain changes? What if I ask for the covariant derivative of the vector field A with respect to some value, some real number multiplied by the vector B? Now, if I understand B to be a vector field and I multiply it by a number A, I'm just sort of multiplying this whole vector field by a constant. But what we're usually talking about is a function on the space-time, a vector field on the space-time, and in this case, what I'm particularly interested in is that function at P and the vector field at P, because as I've said several times, all that matters is at a certain value, at a certain point in the space-time manifold. So I'm curious about how this derivative might change if I multiplied the vector field B by some arbitrary function on the space-time, where we always assume, of course, a smooth function. And you could imagine that if you were doing regular calculus and your independent variable was x, and you suddenly converted x to, say, 3x, right, you would imagine that the derivative, well, let's say you had the function x squared, but now you're changing x to 3x, so the derivative of x squared would be 2x, but the derivative of 3x squared would now be 6x, right? So we're interested in this idea that, well, it should be multiplicative, right? Because that's sort of the dependent or the independent variable in a sense. That's the direction of change. So we're going to embrace that, and we're going to insist that this is got to equal this. The directional derivative of A, when all you've done is scale B, is going to be the scale of the directional derivative of A in the direction of B without the scaling times the scale factor. And remember, this guy here, right, that's a vector, an element of the tangent space at S, a tangent space of the point P in S. And this is also a vector, the element of the tangent space at X. It's not, and this is a real number, and you're allowed to multiply vectors by real numbers as long as it's a real vector space, right? That's the whole point of a real vector space, is that you can multiply it by scalars, and in this case the scalars are the real numbers. So that's what this expression means. Write it again clearly. This is an axiomatic statement. This is a demand we make on the nature of this object. So that's one thing. That's how you scale F. But now the question is what about scaling A with the same kind of function? What if I did this? F A, where I'm now taking the directional derivative of the vector field F A in the direction of B. Right? So now it's the same thing. A is a function of X. F is a function of X. So this whole thing is some new vector field X, which is a function of X, right? I guess I have to track the vectors if I'm going to use X redundantly, or I could make this a small scripty X or something. So what about this guy? Well, we want that to behave the same way you would have the product rule behave. It's got to behave in with the Leibnizian rule. Let me erase this so I have some room. And so this guy has got to be the directional derivative in the direction B of, let's see, how do I want to write this? I want to write this of F times the derivative times A plus F times this, right? So this would be the Leibnizian rule, where I'm taking the derivative of the first factor and multiplying by the second factor, and then the taking the derivative of the second factor and multiplying by the first factor. So these two rules are telling us how things operate, but we kind of need to understand this. And what would be if we imagine our manifold, right? We have the manifold S, we have the point P, and we have some function f on the manifold. And f doesn't have vector components. F is just a number at every point in the manifold. And its derivative in the direction of some vector or some tangent vector along some curve, which would be b in this case, that is simply going to be the directional derivative of a function f with respect to its coordinate system. Now, we already know that all vectors b that are elements of the tangent space at p, they are differential operators. So we can now talk about the operation of the vector b on the vector f, right? And that will give us another function on the manifold. The derivative, the partial derivative, is basically a partial derivative of f on the manifold. If we went to, and that would be in the CFREE notation. Right? In the CFREE notation, we would write it this way, or we would just write it bf. And it's understood that we're taking the vector b and applying it to the function f to get a new function. In the comp notation, we would write, oh, well, b is simply b mu partial mu f. So this guy is going to simply be b0 partial 0 of f plus b1 partial 1 of f plus b2 partial 2 of f plus b3 partial 3 of f. And then this is going to be df dx0, b0. I'm just expanding the notation a little bit. b1 dx1 of f. And here, if I really wanted to go right, I would do f of x0, x1, x2, and x3. And this is simply the partial derivative of f with respect to the variable x1, of which it is a function, because it is a function on the space-time. And here I've broken the space-time into a specific coordinate system, and this derivative is easy to take. And b, the vector b, is literally defined by this process on some arbitrary function. Well, in this case, we would use it on the function f. So this guy is very easy to understand. So let me move this stuff out of the way, and I will now write b operating on f times a plus f in the partial, covariant derivative of a with respect to b. Now notice how everything works here. This is a function times a vector. This is basically a real function. Well, let's see. The way if I was like a real textbook guy, I would say this is a c. We'll always say infinitely different. A c infinity function on the manifold f times an element of the tangent space at S, which is simply a vector. So this is a vector, and this is as we've just shown, this is the derivative. This is basically a differential operator acting on a function which returns another function, so that's also c infinity on S, and this is an element of the tangent space at S. So this is a vector. So that's a vector plus a vector, and it's all done at the point P, or at some point on the manifold, and presumably can be done at any point on the manifold where all of our conditions are met. The conditions being that A is a vector field defined on that point, F is a function defined A is a vector field defined in the neighborhood of all the points. F is a function defined in the neighborhood of all the points. B is a vector field that it has some value at the point. Though it doesn't have to be defined in the entire neighborhood of the point. It does have to be defined along some curve, but that's what a vector is. A vector is, the way we've done it, a vector is always defined on some curve by its very nature. So these two rules can now be, I should just rewrite them at this point. This A equals F delta B A, and this FA equals, I'll do it A, I'll put the F there, plus B acting on F of A, right? These two rules are sort of our axiomatic foundations for the behavior of this idea, of this covariant derivative type operator. And so I've rewritten these rules here, and of course when I say these are the axiomatic rules, I'm forgetting two critical ones, which is the statements of linearity, right? So B plus C, so the directional derivative of A in the direction of, or the covariant derivative of A in the direction of B plus C, which is another vector, B plus C, that's going to always equal this. And likewise, the directional derivative of A plus C in the direction B is going to be the directional derivative of A in the direction of B, I'm sorry, the covariant derivative of A in the direction of B plus the covariant derivative of C in the direction of B. And these are the axiomatic rules that really define the full behavior of the vector BA. And you'll notice it's always in terms of itself, right? So, you know, BA shows up here. We just know the rules of how it behaves. This does give us a hint on how to do our conversion from the CFREE, which is what this all this notation is CFREE, coordinate free, into the comp notation, which is the coordinate-based notation involving components. And you can see a couple examples that are worth diving into. For example, if I substitute B equals, let's say, B mu partial mu. Say we use that. We're in the full component notation. We've selected a coordinate system. We've now got the coordinate basis, and the vectors are now all identified with differential operators. Well, let's go to the first rule, right? The first rule would say this B mu partial mu of A, right? Well, actually we need to go to the third rule first, right? Because this is simply B0 partial 0 plus B1 partial 1 plus B2 partial 2 plus B3 partial 3 of A, right? So, but now I'm going to use this rule and just break that into, well, I'll do it all at once. So I'm going to use this rule and this rule. Because remember, this is a function of x. The components are a function of the manifold, and the basis vectors are our partial derivatives taken at a point on a manifold. So these basis vectors are all elements of, well, maybe not TP, maybe I should say TX on S. And then this is a function on the spacetime. The components are a function on the spacetime. That's why this is a vector field, right? So F becomes B0, and B becomes the partial of 0. And I'll just do a combination. B0 partial 0 of A plus B1 nabla partial 1 of A plus B2 partial, nabla partial 2 of A plus B3 nabla partial 3 of A, which in almost every book you'll see is going to write that as B0 nabla 0 of A plus B1 nabla 1 of A plus B2 nabla 2 of A plus B3 nabla 3 of A. They're going to suppress that partial in the subscript. And this, generally books try to do things where you're not dealing with subscripted subscripts, right? If you can get away without doing it, you should. Now, LaTeX does a pretty good job with it, so I don't worry too much about it when I write stuff in LaTeX. But anyway, the bottom line is this is going to be B. Now you take this and you collapse it using the Einstein sum, and you go B mu nabla mu of A, right? And so that's a step towards this comp notation. It's not the full comp notation. We still have to realize that this thing ultimately is going to be B mu A, and then this is a vector, right? This is a constant. This is not a constant. It's a field, right? It's a real field, a function on the space-time. This is a vector field, so it's going to be B mu, and then this will be A nu covariant derivative mu, and then to preserve its vector nature, you might throw down the vector itself that sums over this nu. But in true comp notation, you don't do that. You leave this out, right? That's the whole thing. So this is actually the binding between the comp notation, the full comp notation, and the abstract notation. So I guess that's worth remembering, right? That's how you're going to switch these things in your mind. The covariant derivative of A contracted on B mu is what this thing is. And I guess another way of, so we can, it's fair to do the full thing out, right? You can go B mu, right? A nu partial derivative with respect to mu plus gamma, it would be gamma alpha and then this has to be, wait a minute, this has to be some dummy index, right? Hold on. This has to be a dummy index sigma, and then mu, and we have to have a sigma, and then this has to match here nu like that. And I think that jives, right? Because what we have is this contracts with the covariant, the derivative index. This contracts with the derivative index there. This is a dummy index, and you're left with mu, right? And so this all clears up to be, yeah. And then in the end, of course, it's a vector, so you would get partial nu out here would be the final vector index. Okay, so you could go that far, right? You could go ahead and substitute to this, and then this would be the full comp notation. Although in the true comp notation, you don't actually have the final vector part. You just know it's a vector because this whole thing ends up being something with one contravariant index, which of course is what we understand to be a vector. So this is how you start applying those rules to convert. You apply these rules with these kinds of substitutions, and you can convert from CFREE into comp notation pretty easily. But you can't get all the way there. This part here, right? Remember, when I made this last line, I actually substituted for this based on our analysis that was done completely in the comp notation a couple lessons ago, where we peeled apart how to describe this covariant derivative of a vector field. So this guy here has to come from left field, right? It has to come from our knowledge of this analysis. So the question is, how do we get at this through this CFREE notation? And the answer there, I mean, the answer that I know, I'm sure there's a bunch of ways of doing it, is to lean on this expression here. And how are we going to do that? So let's try it. Let's go back to, I'm going to write down the covariant derivative of A in the B direction, and then I'm going to make the substitution covariant derivative of A in the B mu E mu. So I won't write partials, I'll use this E vector. and then I'll write A nu E nu, like that. So I'm going to use both of these expressions to decompose this thing. And so I'll begin with the easy one, which will be B mu E mu A nu E nu, like that, where I've kind of used a combination of this and this, just like I did down here, right? Where, you know, I broke it all down into, I used the linearity and then I recollapsed it back into this thing here, right? So that's sort of what I did. And you could also alternatively write this is with getting rid of that mu, A nu E nu, like that. I should be a little clearer here because I want to proceed with great clarity. So you could write it that way. I'll stick with this for now. So then you use the Leibniz rule, right? So now I have B mu, and this will be, let's see, so the Leibniz rule is going to start with the covariant derivative in the direction of E mu of the function A nu times the basis vector E nu. So this is a, and then plus A nu times the covariant derivative of E mu in, or the covariant derivative of E nu in the direction of E mu. So now let's sort of do our analysis here. Remember, A nu is a function, right? It's a function on space-time. We probably call it an infinitely differential function on the space-time. So we have a definition for this. We know that the covariant derivative of a function is just the vector operating on the function. So now we kind of have to go back and think of these vectors in terms of vector operators, or of differential operators. So we'll go with E mu is partial mu, right? And we'll do that for all the vector functions, or all the vectors themselves. So this becomes B mu times the partial derivative, the muth partial derivative of A nu, expressed as with the vector basis E nu, plus A nu, and then we have this thing, the covariant derivative of E nu with respect to E mu. So it's this guy that we can't really reduce any further, right? So we're sort of stuck with that. And in our system of abstract notation, that's kind of where the whole thing bottoms out. So we need to be able to convert this thing into the comp notation. And we just do that by sort of fiat definition. We're going to say that that is equal to gamma alpha. Well, first of all, we know it's a vector, right? This we know is a vector, right? Unlike this guy, which is a scalar function because it's the covariant derivative of a function. Right? It's not the covariant derivative of a vector. The vector part was left out here. And it was the Leibniz rule that now we're dealing with the covariant derivative of the vector part, which is a vector. And of course, it's times a function. So everything works out. You have a function times a vector, which is another vector, and you have a function times a vector, which is another vector. You're summing two vectors using the addition rule of vectors. And then you're, again, multiplying by functions. And ultimately, again, this whole thing is presumably a vector, so we would have at the back end here partial mu, or E mu, depending on what phase of our process we're in. So this guy here, though, it's a vector. So we are going to say, being a vector, it's going to be some set of components times E alpha, right? That's what a vector is. So this vector in component notation is going to be some coefficient times summed over the vector, just like we always do. But clearly this has two indices, mu and nu. So we are going to give this guy mu and nu, like this, and now it is a this is a vector. It's got all the indices are accounted for. It's got the mu, the nu, and the alpha. So for example, if I was interested in E mu 0 of E2, then this value would be gamma alpha 2 0 E alpha, right? And we would just have to execute the Einstein sum, so it'd be gamma 1 2 0 E1 plus gamma 2 2 0 E2 plus gamma 3 2 0 E3 gamma 0 2 0 E0, right? And that's what this would equal to. And that is a vector. It's got all the components it needs, and this thing equals that thing. That's our definition. That allows us to bridge between the CFREE notation and the comp notation. And then, you know, we could push this a little bit further, and we could something's missing here. Something's missing. Hold on. Oh yeah. So the B mu comes out. I need the B mu over here, right? I need a B mu right there. And then ultimately, I guess this whole thing in principle needs to be given the leftover index is nu. Yeah, the leftover index, if I take that out there, I could put that out over here. And I think that accounts for everything. No, actually it doesn't. It doesn't. I'm sorry. I can't do what I just wanted to do. The E nu has to stay here because this guy here is a vector that has its own basis. And so this is about as far as I can break this down. Well, okay, so how would we go all the way? I guess we should just go halfway, right? So let me redo this. This is B mu, and then it's A nu partial mu. I'm going to use the single line notation to capture what this is, right? That's equivalent to A mu partial, or nu partial mu. And then I'm carrying around these basis vectors, so it's got E mu as the basis vector. Now I'm going to substitute in our comp notation here, so I get A nu, the way I've done this, has A nu there, and B mu, and then it's going to be gamma alpha nu mu E alpha, like that. So there's a lot of dummy indices here, right? So I want the alpha to be, I want to pull out this vector here, and I want to pull out the B as well. So I need to change the alphas to nus, and in this expression here, I want to change the alphas to nus and the nus to some other number. So I'm going to do that. I'm going to go B mu A alpha mu E nu plus A delta B mu gamma nu, and I changed nu to delta, so this is a delta, and this is a mu, and this is an E nu, right? So all I've done is change dummy indices. You got to get used to that, right? If you're summing, these mu's, I could call them anything I want. These nus, I can call them anything I want. These alphas, I can call them anything I want. But if I call them the same thing as they are over here, and if you actually worked all this out, you'd notice that that actually is okay. I can actually pull things out and distribute. And I would end up with A nu partial mu plus gamma nu delta mu A delta, and then this would end up being B mu E nu, like that. Phew. And and then in true comp notation, we eliminate this altogether, and this ends up just being A nu covariant derivative with respect to mu, B mu, right? And and then this has a leftover, an unpaired covariant or contravariant index because we've abandoned this, so there's no pairing for it. And we know that anything with an unpaired contravariant index is just, we call it a vector in the pure comp notation. So that's how we make that link to the comp notation. One thing you should notice that Meisner, Thorne, and Wheeler points out is that the ordering mu, nu flips, and you go with nu, mu on this definition. I'm not sure why. I'm sure that eventually, if we work with this enough, we'll see that that's a convenient choice, but I'm not quite sure why that is. All right, so with all this in mind, we can quickly do the rundown of the different notations we're dealing with. I can't get away from liking to do that. So we have the covariant derivative of A in the pure comp notation. And the covariant derivative of A, oops, this should be a mu, sorry, in the direction of B looks like this. This guy in the abstract notation looks like that, and this guy in the abstract notation would just look like that. In the Meisner, Thorne, and Wheeler machine notation, it's a blank with an A right here, and this guy is a blank with an A vector field. Well, this is a vector field, and some vector B right here, all at the place B. This one can also be abbreviated by overloading with just A and B, two vector fields, right? And that's the same thing. And ultimately, given that this thing is a vector, the presumption is that if you put in some one form right here, you could turn this into omega delta B A, which is a real number, right? Again, this notation is very, very rarely used. It's more of an expository thing to sort of teach you how to get to this point. That is the different varieties of notation that we're going to be dealing with here, I think. But I do think while we're at it, while we're here, why don't we have a quick look at something that will ultimately become very important. The directional derivative of A in the direction, the covariant derivative of A in the direction of B minus the covariant derivative of B in the direction A. We already hinted about this in the last lecture. But if we were to do this and break this down into the comp notation, if we just the full breakdown into the comp notation, what would this look like? And the answer is it would look like this. B nu A mu nu plus gamma alpha, and then I have to come up with another symbol. Why don't I put gamma here, nu, and then A gamma. And this is, in order to be a full vector here, I have to go partial mu. Wait a minute. Mu partial mu, like that. Minus, and then I have to kind of do the same thing. A nu B mu nu plus gamma mu little gamma nu B gamma, and then this would be partial mu, right? And then I just start combining all this stuff, right? And I get B nu A mu nu plus, well, not plus, let's do let's do the let's subtract from this guy the first term over here. Let's do that one. So it's minus a nu b mu nu, like that. And then we'll add the first term on the left side, b nu gamma mu gamma nu, and I'm gonna pull out these guys for now. They're both the same. The partial mu's of the vector basis. I'll pull that out. So then this would be gamma mu alpha gamma, and then minus the same thing would be a nu gamma alpha gamma nu b gamma, right? And then this whole thing will have a gamma mu at the end. And then let's see what happens next. So we want to have a close look at these two terms, right? Because ultimately what you have is some dummy indices. Actually, yeah, this index is screwed up. That should be a mu, right? This I don't know why I have an alpha there. So yeah, see, it's this term comes from here, which is mu gamma nu, and this is mu gamma nu also, right? So now we look at these two terms, and we're going to make it so that their indices are comparable. And the way we do that is we are going to exchange, we want beta and gamma to be the same. We want, okay, yeah. So what we want is I want to make the indices of B and the indices of A the same in both of these two terms, which means I have to sort of make a change. Now, the good news is that the nu here and the gamma here are dummy indices, so I can name them anything I want. So I'm going to change nu with gamma, so this A has a gamma on it, and then I'm going to change gamma with nu, and then this B will have a nu on it. And you understand, this is a dummy index. I can literally name it anything I want, so there's really no trouble doing this. So this term is going to end up being A gamma, capital gamma, and then the gamma is going to become a nu in a moment, but the nu will be a gamma, and then B, and the B's gamma will become a nu, and then this gamma will become a nu, right? So this term, that is exactly the same as that. It's simply just renaming the indices. But what's nice is I can now kind of compare these two things, and I end up with, well, everywhere now, B's got a nu on it everywhere, nu. That's the derivative. A's got a nu on it here. Well, that doesn't matter, actually. It's just these two terms that matter. And so the question is now, is there anything further we can do to simplify this term with that term? So we end up having a, let me write it all out, B nu gamma mu gamma nu. I'll bring out the A gamma up here, and let's see, to make the comparison good, I'll make this, why don't I can see, everything commutes when you have these nice, so I'll make this A gamma B mu, and there's a minus sign. Okay, so this is what, this expression right here is exactly the same as that pair up there. So this thing would cancel if gamma mu gamma nu minus capital gamma mu nu gamma. If that equaled 0, then this would go to 0. In other words, if this equals that, because this and that are the same as this and that. So if this equaled that, then it would be, this whole thing would cancel, which is tantamount to saying that the connection coefficient is symmetric in the lower two indices, right? If that were true, then this whole thing here would cancel, and all that would be left is this would equal this. So it turns out that it will become another assumption of general relativity that this connection, that all connections involving general relativity have this property, that the connection is symmetric in those lower two indices. And that is called torsion-free. Torsion-free. That means the torsion tensor equals 0. And we haven't defined the torsion tensor, but eventually we will. It's just too tempting to go this far and not at least demonstrate this little point. It's also a bit of foreshadowing that'll help make later stuff a little unsurprising. So ultimately, we want this property. We want all general relativity to have torsion-free connections. Now, there are alternative theories to general relativity that do have torsion-full connections. We're not going to discuss any of those, and there's really no particular evidence right now that they're very useful theories. That is, there's nothing we know of that isn't pretty well accounted for by regular general relativity. That's an arguable statement, I'm sure, but this is a class on standard general relativity, which always involves these torsion-free environments, which is an assumption of the theory, ultimately. So this thing here ultimately equals B nu A mu partial nu minus A nu B mu partial nu. Notice that these do not have covariant derivatives. These are covariant derivatives in certain directions, but ultimately in a torsion-free environment, it's actually equal to the difference of two terms involving partial derivatives, right? And we give that a symbol. We call that B comma A a Lie bracket. This is called the Lie, well, the Lie bracket of B and A. And we put B first because it's kind of B, A, B. And we all know that the commutator, or you should know that the commutator of B and A would, in operator form, would be BA minus AB, which is opposite of the commutator AB. So it does matter. But in normal operator notation, that's what you get here. We're kind of mimicking that because the B is here first. So it's kind of like del B, then A, minus nabla A, then B. It's just the way the notation works. So that's an important little extra thing to do. So that actually basically just finishes up our analysis of this part of the CFREE notation. And notice how we always really, when we developed this notation, the CFREE notation, we kind of always go back and lean on the comp stuff to help us understand it. And that, I think, is pretty much a universal facet of general relativity's CFREE. You can do a lot of interesting things in this notation, and it's very, very useful to speak of things in generality that way. But when it gets down to the grind, you always kind of go back to this, and you really need to be able to look at this and immediately convert it to this in your head. Well, not literally in your head, but this is intimidating. This seems to be intimidating, but we actually work hard to understand it. You can leverage all that hard work you did to understand the comp notation, and you should be able to immediately apply it to the abstract notation without having to sort of recreate an entire new analysis of the subject just in the abstract. Although we are going to do that, we're always going to be making this conversion, leaning on this conversion to understand things. Okay, so what will we talk about next time? Right, so the next topic that we are going to get into, not in this lesson, but the next topic is going to be the topic of parallel transport using the CFREE notation. So CFREE parallel transport. That's next. And the basic principle in CFREE parallel transport is basically that the covariant derivative of a vector field A along some curve whose tangent vector we give by, we'll gamma dot tau. If the curve is gamma tau, we're going to say the tangent vector of that curve at, at a certain point is gamma dot of tau. That would equal the, say, I guess what we've been calling b here, right? It's very simple. It's just the tangent vector of a curve. Whenever we put in b, we are implicitly assuming that b was the tangent vector for some curve, right? So we just write, now we're going to, instead of talking mostly about the vector, we're going to emphasize the curve, and we're going to specify the tangent vector of a curve. So now we're going to say the covariant derivative of the vector field A, right? So we have some, here's our point P, here's a neighborhood of P. On this neighborhood of P, we have a vector field, which is A, and A has a value at P, and it has a value along this curve as well, right? It may change a lot, may change a little bit. But, so maybe if I point out A just along the curve, right? And the question is how does the vector field A change along this curve gamma? And the key to that change is not the whole curve itself, but just the tangent vector of that curve at every spot, right? And that is what we mean by this term, right? So we're emphasizing the curve. And when the covariant derivative of A with respect to this curve, the direction of the curve, if that covariant of A with respect to that curve equals 0, if that equals 0, then we say that the vector field A is autoparallel. Autoparallel on gamma. And so we're going to talk about that we're going to start talking about that in our next lesson and understand the notion of parallel transport in terms of this abstract coordinate-free notation. So see you next time.